All right, so welcome to lecture 21. So today's lecture is going to be the final lecture in the Star Tracker unit that we've been doing for a little while. And it's going to be on something called Wahba's problem. And so let me share my screen and we'll take a look at the notes from the past couple of days. So if you're getting sick of seeing me talk about the kind of recap from the beginning of lecture 18, sorry, because we're going to do it again. If you're like me, you need something explained to you about 30 times before it starts to stick. So hopefully some of you all appreciate the repetition. But these are the four lectures and the four major topics in the Star Tracker unit. So the first of these is processing a star field image so that we can actually turn like bright pixels in an image to line of sight directions to stars. So you get star unit vectors in your local frame. Then we, ask our astronomy friends about a star map. And so there are maps of stars. The Hipparcos catalog is an example of a star map. And we can use the six astrometric parameters. We don't necessarily need all six, but there are six of them. We can use those to reproduce the line of sight directions to the star in the global frame, in this case, the International Celestial Reference Frame. But then that leaves us with a correlation problem. So which stars in the image are which stars in the catalog? And for that, we use invariants, which are name tags, numerical name tags that we give to asterisms or groups of stars in an image. Say, well, look, here's a triad of stars in the image, and that has these interstar angles. Let me go find a catalog triad with the same interstar angles. And if it looks similar, that's a match hypothesis that I can then go verify either by reprojecting the catalog into the image or using something called the pyramid star ID algorithm. So we talked about those. Finally, you've got the stars in the local frame, you've got the stars in the global frame, and you know which ones are which. You've set everything up. Now you just got to knock it down by solving Wahba's problem, which is the actual attitude determination part of all of this. So hopefully people are waiting with bated breath because this is the last lecture that you need to really nail homework 4. So we're going to go over the math. And I think I've alluded to this before, but it's going to be a pretty long and drawn out derivation followed by a shockingly simple procedure to actually solve Wahba's problem, which I believe can be done in as little as 3 lines in MATLAB. So we'll see. We'll see if I can actually keep to that promise. But so, any questions before we get into today's topics? Any questions on that overview? All right. So just to put that in words or put that on the paper, we can process a star field image to get local line of sight directions to stars. And we're going to use this notation. We're going to call those U, the letter U with a hat, meaning it's a unit vector of the ith star in the camera frame, and it's noisy. So a little tilde on top there. Similarly, we can download a star catalog, and create an invariant index. Those of you that have started down that road already, definitely the devil's in the details and it's easier said than done. So make sure that you allot plenty of time for yourself to do that when you're doing homework 4. Ultimately, we can find, or we have, corresponding catalog star. These are global line of sight directions. And so this is going to be U with a hat because it's a unit vector of the ith star in the inertial frame. That's going to be our notation today. So finally, the question is, what is our attitude? And so here's the equation, right? If we're going to say Ui in the camera frame with noise is some attitude transformation matrix from the inertial frame to the camera frame times UII with a little hat on it, plus we're going to use epsilon as our noise vector. And this is what we're after. We're after this. We want T. And so here's a little diagram just to make this all abundantly clear. And this is a case of there's absolutely no pictures in today's lecture, and I wanted there to be at least one example of Paul's kind of substandard artwork. So let's do a little color code here. You've got line of sight direction to a red star, and we'll just do red, green, and blue probably. So line of sight direction to a blue star, and line of sight direction to a green star. But we also know that in some catalog that the green star is this way, the red star is over here, and the blue star is over here. So it's abundantly obvious as drawn which way the camera has to be facing, right? So it must be the case that the camera is looking this way. And that's what we're going to try to formalize today. So this camera has to be looking at this star, looking at this star, and looking at this star. So we've got in the image, and I guess maybe these should have a little box around them because these are image stars. So we've got the image, we've got the catalog, we've got the match that's implied by the color coding. So now we've got an attitude estimation problem. Okay. So we are going to pose this as an optimization problem. So at this point, we've seen a couple of optimization problems. Even if y'all haven't taken Dr. Hickens' design optimization or some other optimization course, we're starting to get comfortable with the idea that we're going to create a function, which is like an error function. That's like, okay, this function is bad if it is large. And then we want to minimize that function. And that usually involves us doing some sort of, what is it? Set the derivative equal to 0, essentially, the first differential condition. So we're going to set up a cost function, which we're trying to minimize. So we will pose this as an optimization problem. Okay, so it's going to look like this. J, which is our error, which is a function of the attitude transformation matrix from I to C, because that's what we're optimizing over, is 1/2 times the sum over I, so those are all of your stars, times what? Well, it's going to be basically this error, right? So if UIC is equal to T from I to C, UII, there's noise, but the noise is zero mean, so on average that goes away. Then wouldn't UIC minus TIC UII, that should be 0? That's basically the idea. So it's going to be UIC minus TIC UII. And it's going to be this transpose, and we're going to weight this with the pseudo inverse of the measurement covariance matrix, which we defined at the end of last lecture. So remember, at the end of lecture 20, we talked about this pseudo inverse of the measurement covariance matrix, which we get using the Quest model. So it looks exactly like this, and we're gonna use this in a minute. So we're setting this up as a kind of weighted. It's basically a maximum likelihood estimation problem at this point because it's a least squares problem. We're trying to write an equation for the error. We're looking at the sum of the squared error weighted by the inverse of the covariance matrix. This is an MLE problem, right? So this is UIC minus T from I to C UII again. There we are. So that is our problem. Now we're going to try to simplify this a little bit because that's a lot. So for brevity, we will write J on the left-hand side. I don't feel like writing J of T from I to C. And then, yep, that's good enough for now. So we want to minimize this. Now let's do some substitution. UIC minus T from I to C UII. All that's left is the error, which is supposed to be, on average 0, right? That's the idea. So there's our error term. So in this case, we can say that J is 1/2 the sum over all stars in the image, epsilon I transpose R inverse epsilon I. Okay, now let's do some more substitution. We're going to substitute in the measurement covariance matrix from the end of our last lecture, which is 1 over the bearing error squared. We talked about bearing error back in lecture 18, I believe, times the identity matrix minus UIC transpose. So we're going to do a substitution. So J is equal to 1/2 the sum over all I stars in the image. And then we've got this epsilon I transpose 1 over sigma I squared I 3/3 minus UIC, and this is the non-perturbed UIC direction, UIC transpose, and then epsilon I again. Okay, so we can simplify this a little bit. Okay, so let's go through and we can move the 1 over sigma I to the left. And we're going to, let's see, I want to make sure I use the same notation that I did yesterday. We're using sigma I. Okay, that's fine. We're also going to distribute the epsilon transpose epsilon into this, into the parentheses here. So we have J is equal to 1/2 the sum over all I 1 over sigma I squared. And then we have in parentheses epsilon I transpose epsilon I minus epsilon I transpose UIC transpose epsilon I. Okay. However, you might remember from our discussion of noise towards the end of last lecture that the noise perturbs the UIC direction. It's essentially a small rotation, but because we're adding the noise, but we're going from one vector to another vector on the unit sphere, then the noise has to be perpendicular to UIC. So based on this, we end up with, just as a reminder, remember that epsilon I transpose UIC, well, that has to be 0, right? Because they're perpendicular to one another. So this simplifies a little bit. This now becomes J is equal to 1/2 sigma of 1 over sigma I squared, epsilon I transpose epsilon I. Okay, so far so good. Now we're going to substitute back. So this epsilon I is really UIC minus TIC UII. We're going to clean this up a little bit. So J becomes 1/2 sigma I 1 over sigma I squared UIC minus T from I to C UII transpose UIC minus T from I to C UII. Okay, so what we've arrived at is exactly the same as our original problem, but we've dropped the measurement covariance matrix and turned it into a simple scaling. So we're scaling by the bearing error in each star, essentially. And so if we want to write this just a little bit more succinctly, we arrive like this. And I'm actually going to write this out a little bit fancy, and then we're going to box it because this is important. So we're trying to minimize J which is a function of t from I to c, which is 1/2 times the sum over all I, 1 over sigma I squared, and then this is just UIC minus t from I to c UII squared. Right? So I'm just writing this in a slightly different notation, but there's no math change between this and the previous box, or this and the previous equation. This equation is going to get a box. So after all of that, we've really made no progress in solving the problem. We've just set it up. We've set this up. So this is Wahba's problem. So this is a formalization, a mathematical formalization of the attitude estimation problem that we were talking about before. So before we were saying, we've got these stars in the image, we've got the stars in the catalog, there's got to be some attitude that makes it make sense. Here's how we put that in the most mathematical way possible. And it's an optimization problem where the cost function is the sum of the squared residuals between the local frame vectors and the rotated global frame vectors, each of those scaled by bearing error or uncertainty in that particular measurement. And that is the optimization problem that we're going to try to solve. So this problem was first formally posed by Grace Wahba, a graduate student in 1965. 1965, that's like the same decade as the moon landing. Yeah, exactly. So this was definitely an area of active research in the 60s. And I mean, Star Tracker research continues today. There's always more advancements that are being made. I remember when I first learned that this problem was posed by a graduate student. I was a graduate student and I felt really lousy because I'm like, gosh, is this what graduate students are supposed to be doing? So if you're wondering how somebody who was in roughly the same position you're in now was at this level, then you're not alone, because I'm wondering that too. Some people are just kind of running at a different speed. But so this was Wahba's problem, and it has since been solved a number of ways. We're going to talk about 2 different solutions, and you're free to use whichever one you like for the homework assignment. One of them is clearly my favorite, and I'm not bashful about my bias in that case. But you're welcome to use either one. But before we move on to the solutions, any questions up to this point? We're all comfortable with this math problem? All right, cool. Let's keep this party rolling then. So the first solution method is solving for the attitude transformation matrix, or in parentheses, you could call this the SVD method. This one is my favorite because it is fewer lines in MATLAB, and because I'm lazy. I mean, I'm efficient and I like to do things efficiently. So we will begin by restating Wahba's problem in vector form. Okay, so all we're going to do is take this equation and write it as a vector and matrix vector equation instead of a kind of a sum of things that you might compute in a for loop. So first we're going to define some matrix A, which is going to be a 3 by n, where there are n stars. And it is defined as follows. It is U1C, U2C, all the way to UNC. So these are your image or your local line of sight directions. And then we're going to define something called E, which is also a 3 by n matrix. And this is defined as being U1I, U2I, all the way to UNI. Okay, so these are the global directions, right? We've got the local directions, we've got the global directions, and we're also going to define a weighting matrix. Okay? And that is W, which will be written as follows. So we're going to scroll down a tiny bit here. This is 1 over sigma I, or we'll call that sigma 1 squared, on a diagonal all the way to 1 over sigma n squared, and it's going to be a diagonal matrix. Okay, there's our weighting matrix. So after we've made these definitions, then Wahba's problem can be rewritten as min j of t. I'm going to start getting sloppy. Instead of writing t from I to c, I'm just going to write t just to save pen strokes. And this is 1/2 of AW minus TEW squared F. And in this case, we should make a point where this operator here is the matrix, what's called the Frobenius norm. Frobenius norm. So because we can't take the norm, we take the norm of a vector. You can't take the norm of a matrix. It's a different operator. It's called the Frobenius norm. And well, we'll just bear with me for now because this is going to get a lot simpler. But things are going to get a lot worse before they get better. But then in the end, you're going to be blown away by how simple this is. So we're going to simplify this even further. And we're going to say further, because I don't want to keep writing the letter W. We'll just define A prime as being equal to AW and E prime as being equal to EW. So those are our weighting matrices. Okay. So then we can rewrite the problem as the min of the cost function, which is itself a function of t, is 1/2 A prime minus T E prime Frobenius norm squared. Okay. So if we're going to do this minimization, the thing is this is going to be a constrained optimization problem. So some of you that are familiar with optimization, if you write a function like this and say, okay, find me the t that minimizes this error, then nowhere in there are we enforcing the fact that t is an attitude transformation matrix, which means it is a orthonormal matrix, right? It is a matrix where each column and each row is a unit vector. They are mutually perpendicular. T transpose T equals the identity matrix, right? So you can say, first of all, the inverse is its transpose, and that would mean that the matrix multiplied by its transpose is the identity matrix. So there's all of these properties of the attitude transformation matrix that are written nowhere in this equation right now. So we're going to add something to our optimization. So we can enforce. So first we'll say this. Remember that T must be an orthonormal matrix. And that means that T transpose T equals the identity matrix. So we can enforce this constraint with a Lagrange multiplier. All right. So what does that mean? First, we'll write the equation, then we'll talk about how, what each term means here. So it's the minimum J of t is equal to 1/2 A prime minus T E prime Frobenius norm squared plus the trace of capital lambda for Lagrange, T transpose T minus I. And so this is our Lagrange multiplier. Okay. So for those of you that are familiar with constraint optimization problems, this is one of the most basic tricks that you learn in optimization. But what we're proper orthogonal matrix with following all the rules of an attitude transformation matrix that somehow does minimize JFT, that's not good enough. We actually need it to be that it minimizes JFT and is an orthonormal matrix, where this term lambda is the Lagrange multiplier, which ultimately becomes something else for us to estimate. So you can think of it almost as if we're adding like a state to the things that we're trying to optimize. But for now, this lambda is going to be coming along for the ride. And then TR is the matrix trace operation, right? The sum of the diagonals. Okay. Because ultimately this whole thing needs to be a scalar that we're minimizing, right? We're taking all this complicated stuff and we're turning it into a single scalar number that if it's low, we found the right T. That's the idea. Okay, let's further simplify. So this Frobenius norm, let's go back to that. The Frobenius norm can be rewritten where if there's just some matrix X, that's the same as the trace of X transpose. Okay, so following that, because we would like everything, there's going to be some kind of fancy footwork coming up here in a minute, but we want there to be as many traces as possible here. So this would be the min J of T is equal to 1/2 times the trace of A prime minus T E prime, A prime minus T E prime transpose, plus the trace of Lagrange multiplier times our constraint, TTT minus I. There we go. Okay. So is everybody hanging along so far? We've got a ways to go, but this is a good kind of pausing point. Everybody buys this equation? You think this is accurate so far? Any questions up to this point? Feeling good? All right, thanks for bearing with me. So next, we're going to use some tricks which you may or may not be aware of already. So let's pause and review some useful properties of the trace operator. Okay. So if we're taking derivatives of traces, we can do some fancy footwork here. And you might be saying, well, Paul, we're not taking a derivative. We just have traces. It's like, but remember, what we do in optimization is we set up a function, and then we take the derivative of that function and set it equal to 0 to find a local minimum, right? That's the idea. So let's say you have the derivative with respect to x of the trace of the matrix A times the matrix X transpose. It's the trace of AX transpose. Take the derivative with respect to X. That's just A. Okay. Now, if you take the derivative with respect to X of the trace of X A X transpose, that is X times A transpose plus A. It's similar to the derivative of AX is just A, and the derivative of AX squared is 2AX, right? That kind of, this parallels it, but we're taking the derivative of a trace of a matrix multiplication. And further, the derivative of the trace of A times X transpose is equal to A plus A transpose times X. Okay. Where in this case, A and X are matrices. And if you think this is really spiffy, and if you're wondering where you can learn more about the derivative of trace of matrix operations, there's a fantastic piece of material out there for you to look into called the Matrix Cookbook, which is Googleable. You can just Google the Matrix Cookbook. I have it as one of my favorites in Chrome because it's page after page after page of remember the trig identities from high school where it's like, how in the heck was I supposed to know that? And it's like, well, if you did know it, it's a cool identity and you can use it for your derivations. It's like this is page after page after page of matrix identities. And some of these are having to do with derivatives of matrices, have to do with the trace operation, derivatives of the trace operation, so on and so forth. So if it feels like I'm pulling these out of thin air, I'm not. I'm pulling them out of the Matrix Cookbook, which I encourage you to go take a look at. Okay, so in light of this, we will expand our objective function. That's the J, right? Objective function is what we're trying to minimize. Before taking derivatives. So this might be the single most epic example of matrix vector calculus going on in this class. I don't know. It's a tie between this and then all the crazy partial derivatives we're going to have to do when we get into the next unit, which is Kalman filters. But this is going to be no joke. So all I'm doing is writing this previous equation, but I'm just distributing everything. That's the idea. So this is going to look like the minimum. I'll be shocked if I can fit this on one line. J of t is equal to 1/2 open curly bracket times the trace of A prime transpose minus the trace of A prime E prime transpose T transpose minus the trace of T E prime A prime transpose plus the trace of T E prime transpose T transpose plus the trace of lambda T transpose T, couldn't fit it on one line, minus the trace of lambda, and then close curly bracket. So let's just kind of scroll up for a minute. You can convince yourself. I don't know if it's possible to fit this all on one line, but all I did was I distributed. So we've got basically a binomial times a binomial. So then there's going to be 4 terms when we distribute. And then over here, this distributes into 2 terms. So we're expecting 6 total terms that live inside of this 1/2. Oh, you know what? I apologize. This bracket goes here, right? Because that 1/2 applies only to the first 4 terms, not to all 6 terms. My apologies. Sorry if you have to erase. Okay, so there is our equation. And again, we've been kind of laboring on this for a while, but if we can now take some derivatives of this and do some other kind of mathematical sleight of hand, we're ultimately trying to solve for t that minimizes this function. So to find the optimal value of t, we apply the first differential condition, which is the fancy PhD way of saying you take the derivative, set it to 0. And that's going to look like the derivative with respect to t of j of t is equal to 0. So this is where, if anybody has not already jumped ship, this is where I'm going to need some assistance. Taking, let's see, it's going to be derivatives of traces of matrices being multiplied. We're going to do this one thing at a time. There's going to be 6 of them total. So the derivative, I'll do the first, maybe I'll do the first 2, and then I'll get help on the last 4. How about that? But start paying attention if you want to catch the trend of what we're doing here. So this is going to be 1/2. So what's the derivative of the trace of A transpose with respect to t? Well, the derivative of anything that is not a function of t with respect to t is 0. So easy money. Okay. Now, what about the derivative of the trace of A E transpose T transpose? Okay. Well, let's go up here. We can think of A times E transpose as some matrix, right? Like it's a matrix times a matrix, but all of that is just some stuff that isn't T multiplying T transpose. So I'm going to invoke this first identity here. So the derivative with respect to X of the trace of AX transpose is A. So I would say that the derivative with respect to T of some stuff times T transpose is the stuff, right? So this is going to be minus 2. Well, let's do one at a time. Sorry, not a 2. Not a 2. I'm getting ahead of myself. This is going to be A prime E prime transpose. Okay. All right. So, brave volunteer to help me with the third one. What do we got? Who's feeling brave today? Uh-oh, is it going to be one of those days? I hope I haven't lost everybody.
I think it's TE prime. No,
Oh, well,
no, sorry. E prime
yeah.
A to the no, A prime to the transpose.
So let's see. So we're going to do the third term. And so the third term is T E prime A prime transpose. But what I would argue is, right, remember what the trace operation does, right? The trace operation is the sum of the diagonal elements of a matrix, right? So the trace of the identity matrix is 3, right? 1 plus 1 plus 1, assuming it's a 3 by 3 identity matrix. So I would contend that the trace of a matrix and the trace of a matrix transposed are the same thing, right? So this is my contention. See if you agree with me. And did I recognize, was that Jacob's voice or am I just going nuts? I could easily be wrong.
It was correct.
Corey, all right, sorry. Y'all have a lot of voice. The little thing didn't show up on my screen. So I would contend, Corey, and bear with me here, that T E prime A prime transpose is the same as A prime E prime transpose T transpose, right? Because if you transpose the whole thing, you shift which ones have a transpose and you shift the order, right? Um, and now it's easy, right? Because now, well, what do we do now, Corey? Assuming we can use that trick.
Then it's the same as the term
It's the
before.
same as the one before it. So now it's minus another A prime E prime transpose. Excellent. Sorry, I cut you off when you were explaining your thing because I was just looking for somebody to raise their hand. I wasn't looking for an answer. Is this roughly what you were saying, or is this off in a different direction?
I was saying E prime times A prime transpose, which
I mean, that's
yeah.
basically it. It's ever so slightly different, but it sounds like you were most of the way there, which is great. Awesome. Okay, good job, Corey. So I'll need somebody to help me with T E prime transpose T again. So what do we do in that case?
I can help.
Yeah, what do you think?
So there's 2 rules we could use, but wouldn't it be E prime transpose plus E prime transpose E prime times T?
Yep, I mean that's basically it. That's basically it. So I'm actually going to be a little bit lazier than you. I'm going to do it like this. So it's 2 T E prime E prime transpose. Because what it really is, let's see here, it's this second case here, right? It's the trace of XA X transpose. In this case, it's X times more than one thing, but it's not a function of X, right? XA X transpose. So this should be T times E prime transpose plus E prime transpose E. I think that's basically what you were getting at. And I'm just going to get a little bit lazy because it turns out that it is symmetric and we can simply just do this 2T E prime transpose, which is good. So excellent job on that. And then let's finish it up with one last step. So these are the derivatives of the trace of lambda T transpose T. So I'll do this one. So in that case, that would be what? Well, if we use this third term here, the trace of AX X transpose is A plus A transpose X. Okay. I would contend then that the trace of AX transpose X would just be A plus A transpose X transpose, right? That's the idea. And so what we end up with is, do I have that wrong? Hang on. So it's going to be lambda plus lambda transpose. Okay. Yeah, I think I might have made a mistake in my notes here because the next step is supposed to be plus this, plus lambda plus lambda transpose T equals 0. So I think, unless I'm just overthinking it right now, and then the sixth term is nothing, right? Because we're taking a derivative. I might have gotten things backwards where there's supposed to be a transpose somewhere. So bear with me. I am going to spend some time during our break trying to figure out why that isn't quite lining up because I am not satisfied with that solution. But for now, take my word for it. This is definitely the equation that we're going to need moving forward, barring some possible transpose issue that Paul might have made somewhere along the line. So I will endeavor to figure that out. But we're going to keep this train rolling. So this is the equation that we're trying to minimize. And we can actually simplify this a little bit, right? So what we're really saying, this 1/2, and so this is really minus 2A prime E prime transpose. And then this 1/2 is going to cancel out with the 2, right? So if we choose to simplify this a little bit, we get what? Well, we're going to get negative A prime E prime transpose plus 2T E prime transpose plus lambda transpose T is equal to 0. Okay, this is where we're going to do some more mathematical, it's going to be substitution essentially. We're going to simplify this equation, which is already not that bad. It's not obvious how we can solve it for T just yet. We can simplify this further. By defining 3 new matrices. Okay, so there's going to be some matrix called P, which is not the covariance matrix, which is defined as E prime transpose. There's going to be some matrix Q, which is defined as lambda plus lambda transpose. And there's going to be some matrix B, which is defined as A prime E prime transpose, which this is actually going to turn out to be the star of the show. I'm not trying to spoil it for you, but this matrix is so important that it has a name. It's called the attitude profile matrix. Okay. And if you look at the dimensions, it's going to end up being a 3x3. So, all right, let's keep on moving then. So now the equation looks like this. maybe a tiny bit friendlier. So negative B plus TP plus QT equals 0. Okay. Still a little bit rough. There's no obvious solution yet, but there's some more tricks that we can use. First of all, I want to point out that while it might feel like we're a long way from home, B is fully made up of things that we know, right? It's made out of A and E. What are A and E? Let's go all the way back up to the top. A and E are the line of sight directions to all of our stars side by side to create matrices. And those are known. Those are things that we come into the problem knowing, right? These are each a 3 by n matrix, so they're going to be very wide and not very tall. And so if we have A times E transpose, then it makes sense to be a 3 by 3. Okay, so B is something we can actually figure out. Okay. T is what we don't know. P is also something that we do know. It's made entirely out of E. Q is based on the Lagrange multiplier, which we don't know. So we're not sure about Q and we're not sure about T. First, I'm going to move B over to the other side of the equal sign. So I'm going to say B, actually everything else moves and then the minus signs switch around. So B is equal to T, P plus QT. And then what we're going to do is we're going to get Q on its own. So we're going to multiply everybody by T transpose, right? So BT transpose is TP T transpose plus Q, and then T times T transpose is the identity matrix. Okay. Now, Q, which is a matrix plus itself transpose, must be symmetric. Okay. Now, this term here, T times P times T transpose, which is really T times E prime transpose times T transpose, also, because of its structure, must be symmetric. Which means if you have a symmetric matrix and another symmetric matrix being added together, then this other term here, the attitude profile matrix multiplied by the attitude transformation matrix transpose, also must be symmetric. Okay. How does that help us? Well, because there are some identities for symmetric matrices that we can use. So we know that BT transpose is symmetric. Whoop-de-doo, who cares? Well, here's why we care, right? So we can say that BT transpose multiplied by TB transpose is the same as TB transpose multiplied by BT transpose. So this is true if you've just got a symmetric matrix. It's that matrix times itself transpose is equal to itself transpose times the original thing. And this simplifies because of the unique structure of T. T transpose T, B transpose simplifies to B transpose. And this is T, B transpose B, T transpose. Okay. Almost done. I realize it looks like we've just gone off on a huge tangent, but actually we're starting to bring it in for a landing here. Now, if you thought that we were going to get away without doing eigenvalues, you were wrong. Next is we can perform eigendecomposition on both B transpose and B transpose B. And if we do that, we're going to get that B transpose is some matrix of eigenvectors, some matrix of eigenvalues, some matrix of eigenvectors transposed, right? So these are the eigenvectors, these are the eigenvalues. And then B transpose B is some different matrix of eigenvectors, but the same matrix of eigenvalues times that different matrix of eigenvectors transposed again. Okay, where D is the same diagonal matrix of eigenvalues for both equations. Okay, So let's go back up to this equation here. So the B transpose, this is the same as saying U D U transpose is equal to T V D V transpose T transpose. Okay. So what does that mean? What do we notice here? U is TV. U transpose is TV transpose. And then this is the same thing. Right? D is the same in each. Therefore, get the little 3 dots. U is equal to TV, or T is equal to U V transpose. Now we're not done yet, but that's basically it. That's basically it. So what we're saying is that the attitude transformation matrix is U times V transpose. Okay, well, what is U and what is V? U and V come from the eigen decomposition of B transpose and B transpose B. Okay, well, what the heck is B? Well, B is the attitude profile matrix, which is A prime, E prime transpose. What are A and E? A and E are the local and the global unit vectors of corresponding stars stacked up into matrices. Okay. Now we're not all the way done. We're going to clean this up a little bit, but like that's kind of it. Like that's we've spoiled the joke at this point, right? We're not quite done though. Let's take it 2 more steps to really tidy it up, and then we've more than earned a break because we've been going for a while now. So in this case, we can say where U and V come from the eigen decomposition of B transpose and B transpose B. Or we can skip a step. It's not a mistake that I use the letters U and V, because that might make you think of singular value decomposition. That's not a mistake. We can also take these directly from the singular value decomposition of B itself, right? So let's say we do singular value decomposition on B, which you can do in MATLAB using SVD. B is equal to US V transpose, where S is a matrix of singular values that we don't really care all that much about. Now, we have to be careful to include the constraint that T is a right-handed matrix. So if we just say that T is equal to UV transpose, it's like, well, I want to add one more step. You could theoretically have a left-handed transformation rather than a right-handed transformation. So we're going to introduce one new matrix, and then we're done. So we can ensure that T is right-handed by introducing the matrix M. And M is defined as follows. M is an identity matrix where the bottom right element is the determinant of U times the determinant of V. So it could be positive or negative, but ultimately it's going to ensure that, and here's our equation, the attitude transformation matrix from the inertial frame to the camera frame is U M V transpose, and that gets the box. Okay, so 2 pages of dense math featuring matrix vector calculus, the matrix cookbook, featuring things that you might not have known about symmetric matrices, featuring all sorts of just, yeah, this is pretty wacky. But ultimately, this is like 3 lines in MATLAB. You define the A matrix, which is things that you already know. You define the E matrix, which is things that you already know. B is equal to A E transpose. Singular value decomposition of B. T is equal to UM V transpose. That's it. So maybe that's 4 lines in MATLAB. But I mean, that's after all of that, who would have thought that the solving Wahba's problem was probably the easiest part of your homework assignment, and the image processing is a bit of a bear. The downloading and working with Eparco's catalog is a bit of a bear. Setting up and then searching the index is a huge challenge, especially if you don't have a background in computer programming and data structures. But this is actually not so bad. So it's about 4 equations that you need. Maybe I'll kind of go back through and I'll put like a little red star on each of the important equations. So we need this equation, so it gets a red underline maybe, and then we need this equation, so it's an intermediate step, and then we need these definitions up top, and everything else is a proof that this is the case. I guess we need A and we need E, and we also need W. And then we say A prime is AW, E prime is EW. Those are your steps. But if you are weighting everything by the same bearing error, then the W actually doesn't buy you very much, right? The W will actually get kind of done away with in the math. So that even the W is optional. Okay, so that was a lot of stuff. We are more than halfway done with today, but today is going to be a little bit of a longer lecture because I've got 2 more pages of dense math of a totally different method that you can use if you want to. But y'all have more than earned a 5-minute break. So why don't we cool it for a couple minutes? I'll be around to answer any questions you might have, but also I want to go back and figure out why that one equation wasn't working in the derivation. Let's say we'll be back. So it's 7:01, but it's really like a stale 7:01. It's like 7:02. So we'll say back at 7:07.
Hey, Paul, can I have you scroll back down to the bottom of what you just derived? Cool, appreciate you.
I had a question before we defined the P, Q, and B matrices.
Yeah.
In the second term, you put 2T E prime transpose.
Oh, whoops. Am I missing the prime?
Didn't we cancel out the 2?
We sure did. Hang on, let me check my notes. Um, yes, no, we absolutely did. Good catch. And you'll notice that it's gone from here, right? Because, like, yeah, there should be a 2 here if there isn't a 2 there. Thank you. I appreciate you.
Thank you.
See, I was worried that, like, everybody had just, like, pulled the ripcord and they're like, man, forget this. But y'all are actually, like, catching my mistakes and everything. I appreciate you. All right, welcome back, everybody. I went through and I dug up my notes from when I first learned this material. I think I learned this in the spring of 2021. And yep, this is what I have in my notes. So I'm still not 1,000% sure why this wouldn't be our fourth term here wouldn't be lambda plus lambda transpose T transpose. Still chewing on that a little bit. I don't have a satisfying answer for you, so just we're gonna put that one on the back burner because we got to talk about the next thing. I was hoping that I would have some like, oh, didn't you know that it's following the such and such convention? But I would need to spend a little bit more time thinking about that. But anyway, let's move on to another method because I believe, and don't quote me on this, go check it. I believe the homework assignment wants you to find the identities of the stars in the image, which is one problem, and the quaternion, which describes the rotation from the ICRF frame to the camera frame, right? The passive rotation, I should say. So I want a quaternion as my solution. Now, the way that I coded it up was I solve it this way. I use the singular value decomposition method, and then I just use one of my well-worn, tried and true T to Q functions that I wrote all the way back when we were doing, I think it was like homework 1 or homework 2. So that would be my recommendation. Or you could use another method, which involves solving for the quaternion directly. So solving for the quaternion, or this is sometimes referred to as the Davenport method. So this solution, there we are. This solution to Wahba's problem was developed by Paul Davenport in the early 1970s. I'm a fan of this guy, obviously, because he's got a great first name. Us Pauls need to stick together. So we're going to start with the same problem, right? So we're going to go all the way back to Wahba's problem. The min J of t is equal to 1/2 times the sum over all I stars 1 over sigma I squared UIC minus t from I to C UI I. And then this should be squared. There we are. Where we're going to start getting sloppy pretty quickly and just call this t, right? Just because there's going to be a lot of pen strokes. So let's start by expanding. So we can expand. Okay. And so this would look like the min of J of t is equal to 1/2 times the sum over all I, 1 over sigma I squared, open parentheses. So this is really UIC transpose UIC. Then the next term is going to be UIC transpose UII. Oh, whoops, there's a T in the middle. There's the transpose T and then there's that other T. I'm sorry. I can't even read my own notes. That was the T. My brain is just off today. Okay. UIC times T times UII. Is that right? No. Okay. Hang on. I was right when I wrote it and my notes were wrong. Can you believe it? All right. Let me fix it in my notes. Apologies. There we go. That is correct. UIC transpose T UII. The third term should be, I'm sure some of you were already getting frustrated at me for making that mistake. Sorry. UII transpose T transpose UIC. And the fourth term is UII transpose T transpose T UII. Okay. Can we simplify this? God, I hope so, because this is already a lot. Okay. Well, here's the thing. Isn't any vector, like a unit vector, transposed with itself? That's just one, right? So that gets a little bit better. Similarly, T transpose T, well, that's the identity matrix. And then U transpose IU, well, same game, right? That's also just one. That's going to simplify a little bit. Okay. And then further, these middle two terms are really the same term, but we just have, no, it's actually the same term twice. Okay, that's right. So if that's the case, we can simplify a little bit. Min J of t is equal to 1/2 sum over all I, 1 over sigma I squared, okay, 2 minus 2 UIC transpose T UII. And then they should get a squiggle. Okay, so these two terms are the same thing except transposed. And because it is boiling down to a scalar, we can switch the order. There's not going to be any problem there. Here is 1, here is the other 1. That's why there's 2, and then this is 2. And these cancel out with this. Okay, So this is a little bit better. So now we have the min j of t is no longer is there a 1/2. It's the sum of all I, 1 over sigma I squared, and then in parentheses, 1 minus UIC transpose T UII. Okay. Now what we're going to do is we're going to distribute a little bit. So this 1 is going to become its own separate term. So we're left with the min of j of t is equal to the sum over all I, 1 over sigma I squared, minus the sum over I, 1 over sigma I squared, UIC transpose T UII. Okay? Now, this term here, the sum over all of the square root of the 1 over the bearing error, all of this is a constant value with respect to t, right? If we pick a different t, it's not going to change. It's going to be the same every single time. We are going to give this a name. We're going to define this as lambda naught, because I don't feel like writing this over and over and over again. Okay, so both terms are scalars. I want to be clear about that, right? You've got a vector transposed with a matrix times another vector divided by a scalar. But when you work this all out, and then there's a sum of those, this is a scalar number. This is a scalar number. So J is a scalar number. So because both terms are scalars, we can take the trace of both. At no extra charge. It's free, right? Why? Because the trace of a matrix is the sum of the diagonal elements. The trace of a scalar is just itself. Okay. But we're going to wind up using some little cheaty tricks. Once we get the trace in there, it's like, oh, well, didn't you know there's this weird thing? And then it turns out you can just do this. And that's basically where this is going, if you didn't see it coming already. So the min of j of t is the trace of lambda naught minus the trace of the sum over all I, 1 over sigma I squared, UIC transpose T, UII. Okay, so we just took the trace. And then it turns out, because this is fun, we can invoke the trace rule of cyclic permutation. What the heck does that mean? So it means that the trace of some matrix A times some matrix B times some matrix C is the same as the trace of B, C, A, and it's the same as the trace of A, CAB is what I was trying to say. I'm getting ahead of myself. It's the same as the trace of CAB. It is not the same as the trace of BCA or BAC, right? It needs to be a cyclic permutation. So you can imagine this is a conveyor belt. The C goes off the side and then it comes up to the front again. Well, that's this case. And then you do that again, you get BCA, right? That's the idea. So these cyclic permutations is okay. So then if that's the case, then we can write this as the min J of t is the trace of lambda naught minus the trace of the matrix T, sum over all I, 1 over sigma I squared, UII, UIC transpose. So we wind up doing 2 cyclic permutations to get T all the way on the outside. Okay. Now here's the spiffy part. Does this look familiar? This is the sum over all I of 1 over sigma I squared, UII, UIC. So this is the sum over all I of adjusting for the bearing error, the local directions times the global, sorry, the global directions times the local directions transpose. Okay. This is actually B transpose. So guess who's back? Back again. B is back. The attitude profile matrix. We arrived at it a different way, but again, we have this B. And I should be clear, this is a B, not a beta, right? Just a B. Okay. That's now B transpose, but it's the same B that we're used to seeing. So this now becomes the min of J of T is equal to the trace of lambda naught minus the trace of T B transpose. All right, I can work with that. So now we're going to recall all the way back from when we first learned about quaternions, because we are about to go into quaternion land in a minute here. Recall that you can take a quaternion and turn it into an attitude transformation matrix by this equation. So we've got the quaternion scalar term squared minus the vector term transpose the vector term. All of that times the identity matrix 3 by 3 minus 2 quaternion scalar and then quaternion vector as a cross product matrix plus 2 quaternion vector transpose. Right? So that is not new. That comes all the way back from attitude representations lecture 6. Oh wow, actually I had that up right now. So this is we learned this back in lecture 6 and it comes back to help us in lecture 21. Almost like somebody thought this whole class through. So now what we're going to do is some fun substitutions. So we can substitute this equation into our objective function. Substitute, I forget how to spell the word substitute. There you go. This into our objective function. And after quite a bit of math, and you know it really is quite a bit of math if I'm skipping over it, right? Because it's like, we go into some gory details in this class. We're going to skip a ton of stuff. And what we end up with is this. And this is just algebra from this point forward. Min J of our quaternion is lambda naught minus quaternion transpose K quaternion. Okay. Now, what is K? So K is where all the magic went, basically. When we did all this fun substitution, there's going to be some matrix K, which is a little bit complicated. K, where K is called the Davenport matrix. And if I was as smart as Paul Davenport, I would have named something after myself by now too. So I can't fault him for that. And it follows this rule. So it's K is equal to mu Z transpose Z and S minus mu times the identity matrix. Oh, well, is that so easy? It's like, Paul, what is mu? What is Z and what is S? All right, well, bear with me for a second. First of all, we should mention that this assumes a scalar first quaternion. Because mu is a scalar, this is a vector, this is a vector. So this is a 1 by 1, 1 by 3, 3 by 1, 3 by 3. So when you're doing your Q transpose KQ, it's only going to work if this is a scalar first. If this is scalar last, you could rearrange this, right? That's the idea. But it matters that we get the order correct. I like scalar first quaternions. That's just my preference. You can do it the other way, and that's totally fine. Now, mu is the trace of B, where B is the attitude profile matrix. Okay. S is B plus B transpose. And Z to the cross product, so it's a Z cross product matrix, is B transpose minus B. So if you compute B transpose minus B, and then you look at the top, like, you've got your 3 by 3, it's going to be this term, and this term is all you need to find your Z vector. Or you could write something which basically undoes the cross product matrix operation. Okay, so what that means is, I realize we've kind of gone into the weeds for a little bit, is that these terms, mu, s, and z, which are all functions of B, the attitude profile matrix, can be used to construct the Davenport matrix, and then we arrive at this problem, okay? So ultimately, K is a function of things that we know. Lambda is something that we don't really care that much about because we know it's a constant. We're not really trying to minimize that. What we're trying to do is find Q, which minimizes this problem. So we're still not done, but we've made a lot of progress. And actually, we're almost done. We've got less than a page of math to go. So we're not done yet. But we have a well-posed optimization problem. There we go. And before we proceed, this is about to start to look a little familiar. We do need to impose the unity norm constraint. So remember how we used a Lagrange multiplier in the last derivation to make sure that when we solve the optimization problem that T would actually be a proper orthogonal matrix. Well, now we need to do something similar to make sure that Q, which is a unit quaternion, is a unit quaternion. So our optimization function is going to look like this. The minimum of J, which is a function of Q, is lambda naught minus Q transpose K Q plus lambda Q transpose Q minus 1. So in any sane world, Q transpose Q minus 1 should be 0, and this term should go away. If we are leaving the realm of sanity and we're getting a non-unit quaternion, this term is going to appear, and then it is going to be punished because ultimately we're trying to minimize this function. So this ought to be 0. Any deviation is going to make it a positive value. Okay, then we apply the first differential condition. So then we apply the first differential condition. And this is where, if anybody's still awake, I'm going to need some helpers with this bit. So the derivative of J, which is a function of Q, with respect to Q is 0, and that is what? So the derivative of lambda naught with respect to Q, that's the easy one. That's 0, right? Because it's not a function of Q. What about the next term? What is the derivative of Q transpose KQ with respect to Q? Anybody remember from matrix vector calculus lecture? Ooh, let's see. So remember when we've done this before, right? If we have, basically ax squared and we take the derivative, we get something like 2ax, right? So what's going to be the matrix version of that? It's going to be no, people are shy today. All right, I won't torture you any further. That's fine. We'll keep moving. So this is Q transpose K plus K transpose. This is the matrix vector equivalent of the derivative of ax squared is 2ax. So you can think of it as 2kq, and we're dropping the q on the right, which is one of the rules that we've seen in matrix vector calculus. When we're taking the derivative of, for example, if it was just a q, the derivative of that would just be a, right? That sort of thing. We drop the q that's on the right, not the one that's on the left, because order matters. So then, okay, let's keep moving because we're not done. What is the derivative of this other term here? So it's lambda q transpose q. Well, the derivative of q transpose q with respect to q is going to be 2q transpose. So this term becomes 2 lambda, can't forget the lambda, q transpose. And then there's another term that's just lambda, which goes away. Right? So ultimately what we arrive at is this k plus k transpose, because k is symmetric, we can really think of it as negative 2 q transpose k transpose plus 2 lambda q transpose. All right, this is about to get really snazzy in a minute. All of this equals 0, right? Because that's the whole point of the first differential condition. Okay. Now, if we get rid of these 2's and we move some things over to the other side of the equal sign, what we get is that q transpose k transpose is equal to lambda q transpose. Okay. Now, I'm going to take the transpose of both sides. So this becomes k q transpose is equal to lambda q. Oh, I'm sorry. KQ is equal to lambda q. There we go. Okay. Does this look familiar? I hope it does, because this is the characteristic equation of an eigendecomposition problem. So this is a eigenvalue eigenvector problem. So it must be the case, and I'm going to write this as Q star, which is like the optimum Q. Optimum Q must be one of the 4 eigenvectors of the Davenport matrix K. Okay, but which one? Because there are 4 vectors that satisfy this equation, right? So k times some vector is equal to lambda times some vector. That is true for when lambda is one of the eigenvalues and k is one of the eigenvectors. There are 4 eigenvectors that satisfy this equation. But remember, this is a minimization problem. So we can't just slap in any old one and then keep moving. It actually matters which one we pick. So let's go back to the minimization problem before we applied the first differential condition, right? And let's look at it just this way, right? It's going to be the min of j of q is equal to lambda naught minus q transpose kq. And we're going to ignore the constraint for now, right? In this case, we could say, all right, this equals lambda naught minus q transpose lambda q, right? That's the substitution that we're allowed to make here. So k, so this is q transpose kq is the same as q transpose lambda q, right? That's essentially what we're saying here. And so we're going to make that substitution. Oh, I took it too far, sorry. Here, and there we are. Okay, we can change the order on this. This equals lambda naught minus lambda q transpose q. Okay, but q transpose q is just 1. So this becomes ultimately lambda naught minus lambda. Okay, but this is a minimization problem. So the minimum of j of q is now lambda naught minus lambda. So it behooves us to pick the largest eigenvalue of k. So to minimize j, we need the largest in value, largest in scale, eigenvalue of k. Therefore, thus, we're going to write this out the fancy way. The quaternion from the inertial frame to the camera frame is the eigenvector associated with the largest eigenvalue of K. And that's it. This gets stars around it. I'm not going to box it. I'm probably going to mess up the box. But so let's review here because we just went through a whole bunch of Davenport math. Let's scroll up for a second. And don't worry, I'm coming back down in case you're not caught up on the notes. So we started with Wahba's problem. We ultimately simplified it to this optimization problem here, right here. And then we can plug in this equation for a quaternion. And after quite a bit of math, which we decided to skip, which is saying something because we don't skip it, we clearly are willing to go into a lot of pain and suffering in the math world here, we arrive at this nicely defined optimization problem where K is the Davenport matrix, which is a function of things which are themselves functions of B. So it sounds annoying, but we can define the attitude profile matrix B the exact same way we did before. And then we can use that to construct the K matrix. And this is just a few lines in MATLAB. Once we have the K matrix, we go through this whole proof to show that the quaternion that we're looking for is the eigenvector associated with the largest eigenvalue of K. So we do eigen decomposition on K, find the largest eigenvalue, find the corresponding eigenvector, and then you're done. And that's it. And so this is an alternative approach to the singular value decomposition solution to Wahba's problem. And either one should work for you just fine. It's just a matter of which one you think. I mean, I prefer the singular value because it is fewer steps to code up, but I mean, it's comparing a small number to a small number. So while this may have been one of the mathiest lectures so far this semester, hopefully you see that it's really only a few lines in MATLAB to get your homework all taken care of. And with that, I just have one last note for you, and then I am out of things to say. Feel free to interrupt me if you have a question. Otherwise, I'm just going to add 2 more bullet points here, and then we're done. So on homework 4, I ask you for Q from I to C. Okay. So your options are to find T from I to C using SVD method, which is the first method we talked about, then convert to quat, or just use Davenport's method. Whatever tickles your fancy. And as a reminder, I would also like the Hipparcos ID for each identified star in the image. And that's it. With this discussion done, you have everything that you need to survive and to thrive on homework 4. I think it was definitely wise to push back the deadline on that. I think that having it due tomorrow would be completely unreasonable. You have everything that you need, but I understand that the devil's in the details when the time comes to code this up. And so I'll be around. We'll have office hours after class on Monday. We'll have office hours next Wednesday. Don't sleep on this. Like, don't wait to do this until Tuesday night because this is going to be a doozy of a homework assignment. I hope that everybody's at least started. I encourage you to work in groups with people on this assignment. And yeah, so that concludes our discussion. I'm going to stick around until the top of the hour in case anybody has questions. But if you're all good, then class is dismissed.